All right, so now that we've kind of reviewed what parametric equations are, we're going to look at how do we do the calculus with it. First thing we're going to talk about is derivatives. All right, so how do we do a derivative with parametric equations? So our normal derivative, rectangular derivative, dy dx, basically since we have two different parametric equations, a y in terms of t and an x in terms of t, I'm just going to do dy dt divided by dx dt. All right, and that's as long as dx dt is not equal to 0. And then for your second derivative, you're doing the derivative of your dy dx. So you're doing the derivative of dy dx, okay, divided by your dx dt. Because again, remember, this is another dx dt down here. Okay, so it's the derivative and then with another dx dt. All right, so let's do an example so that you can see what that looks like. So in this first example, we're going to write the equation of the tangent line, the parametric curve at point root 3, 1, and those are our parametric equations. So what do we need? Well, for our tangent line, we need the derivative, right? So we need our dy dx, and we need to evaluate it at that point. And then we're going to use that point. Okay, so let's do the dy dx part. So we need the dx dt. So if I do the derivative of 2 sine of 2t, derivative of sine is cosine. And then I have to do the u, so I have to do the derivative of u, so I do chain rule. All right, so that's going to be 4 cosine of 2t. And then my dy dt, so derivative of 2 sine of t, so that's just 2 cosine of t. So my dy dx is just going to be dy dt, which is 2 cosine of t, divided by 4 cosine of 2t. If we simplify that a little bit, that'll be cosine of t over 2 cosine of 2t. Now we have to evaluate this at this point. Now this point is an x-coordinate and a y-coordinate, but my dy dx is in terms of t. So I need to figure out at what t, what is t when I have x equal to root 3 and y equal to 1. So all we do is set that equal. We know what the x should be equal to. So I'm going to have square root of 3 is equal to, I'm using this parametric equation, 2 sine of 2t. So if I divide by the 2, I have square root of 3 over 2 is equal to sine of 2t. All right, so where is sine equal to root 3? Well, 2t, remember this is 2t, not t. 2t will be equal to pi over 3 or 2 pi over 3. And we'll talk about which one it should be in just a minute. Let's do the dy dt, or I'm sorry, not the y. The y coordinate is 1, so I'm going to set 1 equal to 2 sine of t. So if I divide by the 2, where is sine of t equal to 1/2? So that means t has to be equal to pi over 6 and 5 pi over 6. Something I forgot to do on the last one, this is what 2t is equal to, so t would be pi over 6 and pi over 3. Sorry, that's kind of small. So pi over 6 and pi over 3 is what we got for x, and pi over 6 and 5 pi over 6 is what we got for y. Now you can see when you solve for both of them that pi over 6 is the thing that's in common. So remember, it can hit this value, this y value of 1 at 2 different points. It can hit the x value at 2 different points, but it's hitting at the same time at pi over 6. Another way to think of it is that square root of 3, 1, this is in the first quadrant. Okay, so we want to pick our answers that are in the first quadrant. Okay, so we want to make sure that that's also happening there. All right, so that's how we got our t. So going back to what we were doing, we need to evaluate this at t equals pi over 6. All right, so we're going to have cosine of pi over 6, and then 2 cosine of pi over 3, because it's 2 times t. So that's going to be the square root of 3 over 2 over 2 times 1/2. So that'll just be the square root of 3 over 2. So that's our slope. So we have the slope of a tangent line, and now we have the point, so now we just have to write the equation. So that would be, in point slope form, y minus 1 equals the square root of 3 over 2 times x minus the square root of 3. All right, and that would be your tangent line. Okay, let's do the next example. Example 2, where does the curve have a horizontal or vertical tangent? All right, so let's think about that. If I have a horizontal tangent, that's going to be when my slope equals 0. So in order for my dy dx to be equal to 0, that means my dy dt needs to be equal to 0. And then for a vertical tangent, my slope has to be undefined, right? In order for dy dx to be undefined, my dx dt would need to equal 0. Okay, so whenever you're trying to find horizontal and vertical tangents, all you're doing is setting the different pieces equal to 0. All right, so let's again find our dx dt and our dy dt. Dx dt, remember, derivative of cosine is negative sine, so this is negative 4 sine of t. And then our dy dt, let me do a different color. Dy dt, it is equal to 4 cosine of 2t. So for the horizontal tangent, remember that's when we set our dy. I'm going to make 2 columns here just to keep it separate. Okay, so we're going to set our dy dt equal to 0. So where is cosine of 2t equal to 0? So 2t, so cosine is equal to 0 at pi over 2, 3 pi over 2. Keep in mind that since it's 2t, normally we just go through 2 pi, but when you have a double angle, you have to keep in mind that we'll be dividing by 2, so we want to make sure we get everything where t is in between 0 and 2 pi. So what I'm saying is, yes, this is normally where we would stop, but we want to just make sure and go another cycle around. Okay, so if I go from 0 to 4 pi instead of 0 to 2 pi, that will help me with the 2t. And then if I divide everything by 2, I'm going to get t is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So you see how these t values are in between 0 and 2 pi. All right, so now we got to figure out, okay, do all of these work? All right, so what I mean is we're trying to find a horizontal tangent that's going to be in the format of y equals something. So I want to have y equals, I'm using my y of t, my parameter, 2 sine of 2t. So we're doing 2 times, okay, if I do pi over 4, that's going to be pi over 2. So 2 sine of pi over 2, which would just be 1. So this is y equals 2. If I do the same thing, so that would be a horizontal tangent. If I plug in the next one, then I'm going to have sine of 3 pi over 2. All right, so that'll be negative 1. If I plug in five pi over 4, then I'm going to get 5 pi over 2, which would bring me back around to 1. So in this case, it's not really getting me a different answer. This is the same as that one. Okay, so these I don't really need. They're going to give me the same answer. Same thing if I do 7 pi over 4. Okay, so my two horizontal tangents are, ooh, I forgot the negative. Sorry about that. Is y equals 2 and y equals negative 2. All right, so now let's do vertical. Vertical tangent is when we set the dx dt equal to 0. So I have negative 4 sine t equal to 0. So that's basically saying when is sine of t equal to 0. That'll be, here we don't have a 2t, so we don't have to worry about the 0 to 4 pi. So in the domain of 0 to 2 pi, that'll just be 0 and pi is where sine t is equal to 0. So now we're going to plug those in, because again, vertical tangents have the equation x equals something. So I'm going to have 4, remember my original is 4 cosine of t. So 4 cosine of t, so 4 cosine of 0, that's just going to be 1. So that's one vertical tangent. The other one is when I plug in pi, which will be negative 1. So this will be x equals negative 4. So I have 2 horizontal tangents, 2 vertical tangents. All right, so now what I'd like to do is talk about vectors. Reminder, vectors are just a way to break down a thing into horizontal and vertical components. So when we have these pointy brackets, I have my horizontal component and my vertical component. So if I have x of t and y of t, those are going to be my horizontal component and my vertical component, and that's talking about position vector at any time t. Now, if I take the derivatives of them, if I do dx dt, dy dt, then that's the velocity vector. Okay, it's still a vector, but because I'm keeping them separate, but it's a velocity vector. So notice that this is not the same as dy dx, right? This is just keeping the dx dt and the dy dt separate. And then if we do the second derivative, then that's the acceleration vector. Okay, so if we think about, we're trying to fill in the blank. Blank is the speed of the object or the magnitude length of the velocity vector. So if I have my velocity vector, and then I have my horizontal and vertical components. Remember, this is my dx dt. This is my dy dt. So if I wanted to know the speed, right, that's also called the magnitude or the length. If I wanted to find the length of that, all I'm doing is doing the Pythagorean theorem. Okay, so my speed or the length or the absolute value of that velocity is just going to be the length of that hypotenuse. So that's going to be the square root of dx dt squared plus dy dt squared. Okay, so that is the speed and the magnitude of the vector. So let's look at an example. Okay, we've got this particle that moves in the xy plane so that anytime t, the position is given by these parameters, so x of t and y of t. So if we want to find the velocity vector when t equals 1, so velocity vector, all you're doing is the first derivative, and you're keeping them separate, right? X prime of t, that's just going to be 3t squared plus 8t. And then if I do y prime of t, that's going to be 4t cubed minus 3t squared. Right? Easy peasy. But it does say find the velocity vector when t equals 1. So I want to plug 1 in for t. So for part A, I want to do x prime of 1. So I'm plugging in 1 here and 1 here. So that'll give me 11. And then y prime of 1. So I'm doing that. I'm plugging in 1 for my y prime. Oops, that's a minus. And that's going to give me 1. So the vector in vector component form, that would be 11 comma 1. So notice when they want a vector, they want it to keep it separate. It's not the magnitude. Okay. For part B, it says find the acceleration vector, okay, when t equals 2. So what do we do for that? Well, now we're just doing the second derivative. So we need to do x double prime of t. So that'll be 6t plus 8. Y double prime of t, that'll be 12t squared minus 6t. And now we need to plug in 2, this time we're doing 2. X double prime of 2 is going to give me 20. And then y double prime of 2 is going to give me 36. So my acceleration vector is 20 comma 36. All right, so now, same idea. The particle moves in the xy plane so that any time t, where t is greater than or equal to 0, so we're not counting negative time, the position of the particle is given by these parameters. We want to find the magnitude of the velocity vector when t equals 1. So now we're doing magnitude. Magnitude is that square root of x prime of t squared plus y prime of t squared. All right, so we got to do the first derivatives. So that's going to be 2t plus 3. Y prime is going to be 3t squared minus 3. So now we have to evaluate those when t is equal to 1. So if I plug in x prime of 1, that would give me 5. If I do y prime of 1, that'll give me 0. So if I'm using that in my magnitude formula, I'm doing 5 squared plus 0 squared. So the magnitude is simply just 5. Okay, so now we've got the derivatives down for both parametric and vector form. Let's look at the next thing. Remember way back in January, we did arc length. That was in section or chapter 7.4. And in the rectangular form, we remember how we derived that, and we did the integral of the square root of 1 plus first derivative squared. Okay, so in parametric form, that's going to look like this. So we're going to keep it separated. Remember, we did a lot of manipulation to get it to look like that, but we're going to keep it separated since we have parameters now. So this just looks like the distance formula. So the dx dt and the plus the dy dt squared. All right, so that's our formula for arc length. And does this diagram look familiar? Yes, I hope so. Yes, it's the magnitude. Or speed. Okay, so arc length is like integrating the speed of an object from A to B, which means that arc length is also the distance traveled by the particle from time A to time B. Okay, so the reason we're writing that out is because that would be a good AP free response kind of question. Describe what this integral means in terms of the particle. Well, that would be the distance traveled by the particle from time A to time B. Okay. So let's do an example. All right, so we've got a particle, we've got our parameters, and we have our interval from 0 to 2 pi. All right, the path intersects the axis twice. Write an expression that represents the distance traveled by the particle. Distance traveled by the particle between the two x-intercepts. And it says do not evaluate. So this would be like a good AP type problem. All right, so when you read the distance traveled by the particle between the two x-intercepts, you should think, oh, arc length. What's that formula? So we're doing that integral from A to B of dx dt squared plus dy dt squared. The only thing is we have to find A and B because those are the x-intercepts. All right, so the particle hits the x-axis. Okay, that's when y is equal to 0. So then we need to set the y component equal to 0. All right, so if we solve that, that'll be, where is sine of t equal to 1/2? Well, we kind of already did that, right? We know that t would be equal to pi over 6 and 5 pi over 6. Okay, so that gives us A and then B. Those are the two x-intercepts. All right, so we know what that part of the integral is. Now we need the dx dt and the dy dt. So dx dt, if we go look back at our x parameter, the derivative of the square root of 3 is constant, so we're just going to have our negative 4 cosine of t. Remember, it's negative sign, so that becomes positive 4 sine of t. And then our dy dt, the 1 is constant, so then I'm just going to have our cosine 2 cosine of t. So we have all of our pieces we need, and all we're doing is setting up the distance. So our distance equals the integral from pi over 6 to 5 pi over 6 of the square root of 4 sine of t squared plus oh, I forgot a negative. That's my bad. I was wondering where I got this negative here. This is a negative 2 cosine of t squared dt. All right, and that's all you have to do for that one. All right, so now let's do another one. Find arc length of the curve on that interval and those are our parameters. So again, here they give us a and b, so we don't even have to do any calculations to solve that. We just need our dx dt and our dy dt. So dx dt is negative 2 sine t, dy dt is 2 cosine of t. So arc length is the integral from 0 to 2 pi of negative 2 sine of t squared plus 2 cosine of t quantity squared dt. Now this one, they said they want us to find it. So now we're actually doing the integral. So we're going to have from 0 to 2 pi. If we square that, that'll be 4 sine squared t plus 4 cosine squared t. I'm going to pull out the 4. Okay, so I can factor out that 4. When I factor out that 4, then I'm just left with sine squared of t plus cosine squared of t. And you should recognize that. That's a Pythagorean identity. So now we're just integrating the square root of 4 because all of that became 1. And the square root of 4 is just 2. So if we do the integration, super easy, right? 2t evaluated from 0 to 2 pi. So that'll be 4 pi minus 0. So our arc length is 4 pi. Now if you think about this, if you look at the graph of this, if you remember how we talked about how to graph these, this is actually a circle centered at the origin with radius of 2. And the arc length from 0 all the way to 2 pi is simply the circumference. So if you wanted to do it geometrically, we know that circumference is just 2 pi r. So that's another way to get 4 pi. Isn't that nice how that works out? All right, so this next one, determine the arc length of the curve on the interval 0 to 2. So why don't you pause the video and try this on your own. The integration is a little bit more involved. You have to do some u substitution, but then I'll unpause it and you can see the answer. Okay, so I didn't get to the final answer yet. I wanted to do a check-in. So hopefully you set it up correctly. If not, pause it and fix it. But at this point, you're going to have to do the integration. So make sure to factor out the t squared. And so we have t and then square root of 4 plus t squared. Now we're going to do that u substitution. I would let u equal 4 plus t squared. So that means your du is 2t dt. All right, so what we're missing is the 2, right? So we have to do the 1/2 compensation. So if I do that, I'm going to have an integral with respect to u. I'm going to have 1/2 integral of, this will just be, this is my du, right? This and this is my du. And I'm going to have u to the 1/2 du. So if I do the antiderivative of that, I'm going to have the 1/2. I'm adding the power, so that's u to the 3/2 power. And then divide by that or times by the reciprocal. All right, so that's just going to be 1/3 u to the 3/2. If I substitute that back in, then that's going to be 1/3 4 plus t squared to the 3/2 power, and I'm evaluating that from 0 to 2. So from there, you plug in. Careful here, when you plug in 0, you don't just get 0, because with that we have that constant 4. So we have 1/3 4 plus, this will be 2 squared, so that'll be 4 to the 3/2 power, minus 1/3 4 plus 0 to the 3/2 power. All right, so that's 1/3. This is 8 to the 3/2 minus 4 to the 3/2. Or if you do it as a decimal, it's about 4.876. All right, so that one involved a little bit more calculus, which is good. I know it's been a long lesson so far, but we have a little bit more to do, and that's the surface area. Surface area, remember, kind of went hand in hand with the arc length. So reminder, a rectangular form of surface area, if it was about the x-axis, we said the surface area was 2 pi a to b r of x of square root of 1 plus f prime of x quantity squared dx. Okay, and then if we did the y-axis, we could do it this way, whatever was more convenient, right? So r of y. And then here we just make sure that we had a function in terms of y, the derivative of that, and then dy. Okay, so for parametric form, think about that. We've got, this is arc length, that square root part is arc length, and then the r of y and r of x is the radius. So if I'm doing that in parametric form, not much is going to change. It's just still going to have the 2 pi. I'm still going to have from a to b. It's just I'm going to have my radius according to the x-axis would be my y coordinate, right? So that would be y of t. And then I would have my arc length formula. Remember we said that's dx dt squared plus dy dt squared. That's just our distance formula. Okay. And then if I'm doing about the y-axis, the only thing that changes is the radius. Okay, so now the radius about the y-axis would be horizontal, and that would be the horizontal component, which is x of t. All right, the rest of it is the same. Okay, notice that they're both in terms of t. So let's do an example real quick. Find the surface area of the curve. We have our parameters rotated about the x-axis, then around the y-axis. Okay, so all we have to do is find our dx dt and our dy dt. So this will be pretty easy. Look at dx dt is a constant. Dy dt is also a constant. Will they always be that easy? No. This is just getting practice setting up the surface area. So for part A, our surface area is 2 pi from 0 to 2. Remember we said if we're going around the x-axis, we're using our y component. All right, our vertical component is our radius, so that's 4t square root of 2 squared plus 4 squared dt. And that comes out to be a pretty easy thing to integrate because this is just the square root of 20. So we can take the 4 square root of 20 out, and we can even simplify. The square root of 20 is 2 root 5, so that would be 8 times 2 would be 16. 16 root 5 times pi. Pulled all of that stuff out of the integral. And then now I'm just evaluating t. Or taking the antiderivative of t. So that's 16 root 5 pi times 1/2 t squared, evaluated from 0 to 2. So that's here, when I plug in 0, I'll get 0. So I just have to worry about the 2. So that'll just be 2. So that's going to be 32 square root of 5 pi. All right, then about the y-axis, the only thing that changes for the y-axis is that radius part. So your surface area is 2 pi from 0 to 2. Now we're using the x of t, so that's 2t. Square root, we already knew that was square root of 20. So that part stays the same. And then again, we can pull all of that stuff out. So that would all come out to be 8 square root of 5 pi 0 to 2 of t. So that's going to be, ooh, I forgot my dt. That's going to be 8 root 5 pi of t squared over 2. From 0 to 2, we know that's going to end up being 2. So then that's just 16 root 5 pi. And there we go. That's parametric and vectors with the calculus.